So in this question we are given a bar which consists of two parts made out of two different metals. So this part, the first part, is made out of gold, and then the second part made out of silver. And then the golden part is held at temperature 80 degrees C, and the silver part is held at 30 degrees C. In steady state, the question is, in steady state, what is the temperature in between? So what is the temperature at that interface between the silver and gold? And we're also given the coefficients of heat conduction for both metals. Well, in steady state, the rate at which the heat is transferred from the interface between these two metals to this side is the same as the rate at which the heat is conducted from this side to the interface. So we can say that at steady state, the rate through the gold is equal to the rate of heat conduction through the silver part. We can then say that this is then equal to coefficient of heat conduction for gold times delta T1 over this distance. So let's say that this is delta X times the cross-sectional area, A. So cross-sectional area of that bar is equal to A. This is then equal to coefficient of heat conduction for silver, change in temperature, delta T2, and this distance is also delta X, it's the same. The cross-sectional area is also the same. The cross-sectional areas will cancel out, delta X will cancel out, then you can say that this is equal to KAU T1 minus T0 equals KAG T0 minus T2. So T1 is at a higher temperature than T0, T0 is at a higher temperature than T2. And these are absolute values, so we should get a positive quantity on each side. Then from here you can just calculate for T0, right? So if you do the algebra here, the value for T0 you get is T1 plus T2, and then there is a ratio of silver to gold divided by 1 plus the same ratio, silver to gold. Okay, then you just substitute for the numbers and you should get 51.2 degree C for the temperature in between. That's it.